I trust everyone watching this video is having a good day or an evening or a night depending on where you are. I am Mr. Ish. Thank you for joining me for this video. When we are looking here at washers, we're talking about everything with respect to double integral procedures where a washer would develop in terms of a cross-sectional slice of that rotational solid. Consider very quickly, when you're doing a basic single integral volume procedure, volume with respect to x or y, let's just say x. You know you're looking from a lower limit to an upper limit, the difference of outer area and an inner area, which is integrated over those limits, and that gives you your volume for that solid. When you look at everything with regards to double integrals, your procedure is slightly different. Imagine we're doing either with x or y. Let's just say, since we're in this video are looking with respect to y-axis, our general integral will be something similar to this, but it won't be exactly this. You will have a to b with respect to dx. A certain double integral will develop. You will have a square and a pi. This here will represent your pi r square, which would be your outer area. And then this will integrate over a set of limits with respect to dy. But when you're looking at this, everything here is with regards to outer something minus inner something. And here your format would be a to b to dx. This of course is a square and a pi. This would be your inner area, your inner pi r square. You can think of it as that. Then that will integrate c to d with respect to dy. But here you're seeing the format kind of mirrors this, but because it's double integrals, it's also different. Outer everything in terms of double integral minus inner everything with respect to double integral will now give you your volume here. Since we have everything here with respect to dy, I've written y over here, and this would be your format with respect to a y-axis rotation. If however everything here was rotating around the x-axis, these things would be flipped around. You would have a dy and then a dx, then you would have a dy and a dx. For this particular case where everything is with dy, you know your equations must be in the x equals format. If you had a horizontal line of rotation, then you know it's y equals format equations. These are the things you just have to keep in mind. Let's look at our question over here. Graph it out. Y equals x squared looks something like this. X equals 2, you know, it's that. Y equals 0, your x-axis. This is the region which is being rotated around the y-axis. You can easily develop a solid which would look something like this in terms of three-dimensional attributes. We can even do that. It would be a rotational solid, and that's what it would look like. And you take out a slice. That slice is indeed a washer, and you've seen things like this before. So it is a washer. Here's your line of rotation, inner, outer, all of that. You remember that. But we're looking here at everything with respect to double integrals, so let's keep it to that. But this is what we're talking about, double integrals where a washer is coming into play. For the purposes of this video, I'm separating everything into two graphs. Watch, my outer graph and my inner graph, and it'll make sense momentarily. My outer obviously is going to be x equals 2 because that represents the further dimension in terms of radius. And we know everything is here limited at the top by what? If you put 2 here in place of x squared, it's going as high as a 4. 2 comma 4. So we know this right here in terms of, we can just say an imaginary y equals 4. That'll be the upper extent of our limit in terms of y from 0 up to 4. You will look across over here, you will have cross-sectional slices which will develop and they'll go up and down like this. That's my outer graph depiction. My inner graph depiction would be something like this, and you know that it'll be the x squared. Here you're seeing discs which will be developing in this way. But notice I'm using the word discs, but we're talking about washers. However, if you superimpose these discs and you now look at the difference of these two discs, the outer disc and the inner disc, you are indeed generating what is a washer. This is just me breaking it down even more for you all. You're seeing an outer larger disc and an inner smaller disc, and their difference is developing that washer. Now let's talk about the double integral aspect. The double integral aspect is nothing out of this world. It's relatively easy. Look right over here. Everything with respect to initial dx going upwards with dy. And why is that the case? Because it's a vertical line of rotation. Your dx integral, both of these limits are tracking straight up, so there's no change. 0 to 2. This will be a square and a pi, pi r square. This will integrate from 0 to 4 with respect to dy, 0 to 4. This here is my outer everything with regards to your double integral for this volume determination, minus. All of this will be a minus, as you can imagine. Now let's do this. Here you have a problem. You're starting out here from a vertex it's very difficult to split it up, but you can work in the reverse from the top down. You know, either way you're coming no further than 2 in terms of the x-axis, so you can imagine this thing was flipped upside down and you would be tracking it from up down. It's alright. This is a 0, that's a 2 in terms of the x. The 0 will stay as is because it's going to track either all the way down or all the way up if you were cheating by flipping the graph, which is alright, there's nothing wrong with that. This limit here will obviously track the curve. It's a y equals x squared. Since we're going vertically, it becomes x equals root y, which will now assume the upper limit. This here all is a pi r square. But that's your pi r square, which will now integrate from 0 to 4 with dy. That's your outer everything double integral. Here's your inner everything double integral. As I have already mentioned, this is my outer double integral. This is my inner double integral. Now let's integrate this. From here you're getting an antiderivative, which is an x, 2 to 0, but it's all in a square. You have a pi sitting outside, 2 square, and you're getting a 4 pi. This 4 pi will become the input for your next integral, which is with respect to dy. 4 pi, you have a 0 to 4 dy. You know, here it's a 4 pi with a y and a 4 and a 0. It's a 16 pi. My outer is giving me here a 16 pi. Let's look at our inner double integral. From in here we're getting an antiderivative x. There's a root y upper limit, 0 lower limit. All of this is a square and a pi. You know, upper limit, lower limit, difference of the two, you'll get a pi y. The pi can push outside as the coefficient for your next integral with respect to dy, with the y coming in, and it's dy. The antiderivative here is a pi, y square over 2, and a 4 and a 0. You can compute this. It's a 16 divided by 2. It's an 8 pi. My inner here is an 8 pi. You know, it's just a difference between 16 pi minus 8 pi is going to give you your volume, and this volume is going to be 8 pi for that rotational solid I showed you at the very beginning. Rotational solid. And of course, I must admit this is a horrible drawing, but this right here was my rotational solid. 8 pi is the volume, and it will be right. I've shown you everything here. Double integral procedure with regards to washers. You're having an outer double integral and an inner double integral, and you're doing their difference, and they'll give you your volume. Thank you for watching.